In this video, we will be discussing the valence shell electron pair repulsion theory, otherwise known as VSEPR, and how this relates to our Lewis dot structures that we have already drawn. The Lewis dot structures that we have discussed in previous videos enable us to determine how things are bound together. But, as we have said before, the properties of molecular substances depend on the structures of the molecules. In other words, the structure determines the property. The structure includes many different factors: the skeletal arrangement of the atoms, which we determine using our Lewis dot structures, the kind of bonding between atoms, which is either ionic, covalent, or polar, which we can determine by comparing the relative electronegativities of the two components of a bond, and the shape of the molecule, which we will use our VSEPR theory to determine. It is the bonding theory that predicts the shapes of the molecules. So what are molecular geometries? Molecular geometries are the three-dimensional structure of objects. Molecular geometries describe the shape of the molecule with terms that relate to their geometric figures. The molecular geometries have characteristic corners that indicate the position of the surrounding atoms around the central atom in the center of the geometric figure. They also have characteristic angles, which we will be calling bond angles. They also have characteristic angles, which are our bond angles. The Lewis theory, which is the basis for the Lewis structures that we've been drawing, predicts that there are going to be regions of electrons in an atom. These regions of electrons should repel each other because the regions will have a negative charge. That negative charge comes from the fact that electrons themselves have negative charge. Some regions result from placing shared pairs of valence electrons between bonding nuclei in the form of a chemical bond. That is a region where the electrons are being shared between the two atoms that are making up the bond. And then you'll have other regions resulting from placing unshared valence electrons on a single nuclei or a single atom. This idea can be extended to predict the shape of molecules. The positions of atoms surrounding the central atom will be determined by where those bonding electron groups are. The position of the electron groups themselves will be determined by an attempt to minimize the repulsion between them. This brings us to our valence shell electron pair repulsion theory, or VSEPR, which is an add-on to the Lewis theory. In VSEPR, electron groups around the central atom will be most stable when they are as far apart as possible. We can think of this as the electrons are repelling each other, and so to minimize the amount of repulsion, they want to get as far away from each other as possible. This is the basis for VSEPR. Because the electrons are negatively charged, they should be most stable when they are separated as much as possible. The resulting geometric arrangements will allow us to predict the shape and bond angles of the molecules. So if we have a central atom and three different bonding pairs, an example of this would be a boron bound to three different hydrogens. You have the bond between the boron, the central atom, and the hydrogen, right, coming along here, and you have this area of electron density, which is going to repel the next bonded hydrogen, which also has a region of electron density. Because you have electrons that are going between the central atom and the thing it is bound to, they repel each other, and they will push each other as far away from each other as possible in three-dimensional space. As a result, you get sort of this triangle shape. We can use the Lewis structure to predict the number of valence electron pairs that will be around the central atom. Each lone pair of electrons constitutes one electron group on a central atom. Each bond also constitutes one electron group on a single atom. This is regardless of whether that bond is a single, double, or triple bond. So if we look at an example of N O2-, our central atom, the one that we're trying to determine the configuration of. As part of our VSEPR theory, we need to figure out how many electron groups there are. An electron group is essentially a region where we find electrons. So for the nitrogen, we have this lone pair of electrons, these 2 electrons which are filling an orbital. These are located in one area of space. Then you have a single bond, which has electrons being shared between the nitrogen and the oxygen. And then you have a double bond. The double bond is a larger region of space, but that region of space lies directly between the oxygen and the nitrogen. It just takes up a bit more space than the single bond does. So in terms of the regions of space where we find electrons, there are 3 different regions. There's our lone pair, our single bond, and our double bond, making up 3 different regions of space. So we have 3 different electron groups. One from the lone pair, one from the single bond, and one from the double bond. Double bonds and single bonds count as 1 electron group each. There are 5 basic arrangements of electron groups around a central atom. Those arrangements are as follows: linear, trigonoplanar, tetrahedral, bipyramidal or trigonal bipyramidal, and octahedral. This is based on a maximum of 6 bonding electron groups, or just regular electron groups, though there are cases where you can have more than 6 on very large atoms. This is fairly rare and beyond the scope of this current class. Each of these basic arrangements result in 5 different basic electron geometries. In order for a molecular shape and bond angles to be considered a perfect geometric figure, all the electron groups must be bonds, and all the bonds need to be equivalent. For molecules that exhibit resonance, it doesn't matter which resonance form you're going to use to count your electron groups, they will be the same. And this is because typically the only thing that differs in your resonance structures is how things are bound together, whether it's a double bond in one location or another. And because your double bonds count as electron groups the same as single bonds do, the electron geometry will be the same.